So, picking up what we were doing on Tuesday, we have this one part of the fundamental theorem of calculus. We have some function, which is an area function. The area underneath the curve from A to some value x of some function. And so this being a function, because this area is not a fixed area, it's area from A to x, whatever x is, x being a independent variable. And we have this idea from the fundamental theorem of calculus that if you find the derivative of this function, you're just going to get back the antiderivative. So I'd like to go over a few problems where we're going to use this. First problem is totally a trick. I'd like you to take a look at it, see if you can figure out what the trick is. It's not a real problem. So I want to find the derivative of f of x equal to the interval from 1 to 2x dx. I mean, it has an answer, it has an easy answer. I just want you to take a look at it, see if it occurs to you what that rather obvious and easy answer might be. So requires no calculation on your part. I hope that's not disturbing. Sorry. This is the function, and I want the derivative of it. Let's see what that is. It looks a little different than this, right? There's an x here. You see this on an exam, you recognize it, you can do one of two things. You can go, oh my God, what do I do? Or you can go, oh, why did he give us such an obvious, trivial question? Anyone see what's going on here? If I made it sound too complicated. What's this thing here? What's the name we give that? It's a blank blank. It's a definite integral. What's a definite? I mean, yeah, sure, it's got some symbols and whatever, but when we're done with this, what do we get? We get a number. What's the derivative of a number? Zero. So if you see something like this, you know, don't be fooled. It's not this. This is a function, right? From a to x, it's integrating some function, some area here. This is just some area, some number, and if you find the derivative of a number, you get 0. Okay. So let's do something that's not so tricky. I have some function g of x, and the integral from 1 to x of 1 over dq plus 1 dt. And I want to find the derivative of g of x with respect to x. Now, this is also a no-brainer, if you see the connection here. Anyone want to hazard a guess? All right, I guess this is a little abstract here. This won't make it any easier, but let's at least, review what we've got here. We have some area function. Area is the area under some number a, doesn't matter, to x, it's a function. We find its derivative, and what do we get? We get this function here. That's kind of what the fundamental theorem is about. We can find areas by finding antiderivatives and evaluating them. So if you have the antiderivative, you have the area function, you find its derivative, what do you get? You just get back your function that you're integrating over. This would be x. You can't get frightened of something just because it looks complicated. You have to think it through. What's going on here? Let's look at something else that maybe looks frightening. 1 to x e to t squared minus t dt. So I have some function. I don't know what this function looks like. Whatever it is, I'm just integrating from 1 to some x, giving me the area. Now I want to find the derivative g of x. What is that? Anyone? Not a hand? Yes, George?
Use the t squared. Same as last time. We used the t squared minus t.
That what you mean? Yeah.
Why is it x though? Why did you use the x?
Well, this is, t is a dummy variable,
Right.
right? After I find the area, it goes away.
Oh,
G of x is the area between 1 and x. So this is a function. It's a function of x, it's an area. Just like any other function, if I find a function of x, if I find its derivative, the derivative is going to be a function of x. Does that help?
you're explaining why the dummy variable goes away.
Well, the dummy variable goes away because we're finding an area. But the reason this is still a function of x is because the original function was a function of x. There's still an x here, right? This is not a definite interval. It doesn't have it's not a number, it's a function. Right? This here is just a definite integral. All right, let's try one more. Call this capital F of x, as confusing as that might be. What could it be? If nobody else raises their hand, I have to assume you're not following me. rather know you were following me before I take the next step. Anyone? Sure.
So we're finding the antiderivative there and then just going back to the derivative of said antiderivative, or that's what we're doing, correct?
Right, I mean, I don't express the antiderivative here.
So
I'm
then-
just expressing, we find the area function, we can find the area function by finding an antiderivative, but I haven't done that step.
So then it should be the same thing.
I'm trying to emphasize that the derivative of the area function is the original function. This is, you know, we get this by finding an antiderivative here. But if we find the derivative of this area function, we just get back our function. So it is,
Is t to the,
t goes away.
oh yes, x, theorem.
Excellent. Okay. All right, I hope that's clear, because to do the next one, you have to understand that, and then you have to go a little further.
Was there like a name for this? Was there like a name to like this area?
The fundamental
Calculus.
theorem
Of calculus.
of calculus. This is what I think this is what the book calls part 1, but it might be part 2. Let's say part 1. Yeah, part 2 says that if you have some function f of x and an antiderivative meaning a function whose derivative is this function, then you can find the area between 2 points by evaluating the antiderivative. This here is a definite integral. It's a number. And how do we evaluate it? We find our antiderivative, and then we evaluate it by the difference in the antiderivative function. But this looks the same as what we're doing, but it's not, because we're dealing with functions here. This is an area function. It has an independent variable x. All right. There's a few more of these I want to show you in case they come up. Some function which is the integral from x to pi, the square root of 1 plus secant of t dt. Now I want to know what its derivative is. Oh, this is a little different. Doesn't look quite the same. What are you going to do about that?
Is it just going to be the same thing but with x but negative?
You make it sound so simple. Yes.
Or
Yeah, because we have this formula that the integral from a to b x dx is equal to minus the integral from b to a f of x dx. Yeah. Yeah, we just change this. Well, now we can use the fundamental theorem, and we can get that the derivative is what? Just negative square root of 1 plus secant of x. All right, now we have one that's truly a little more tricky. Here we have a function which is the integral from 0 to x squared. Oh, I'll have to figure out what to do about that. And well, we don't have some simple trick to do here, do we? Well, think about that for a second. I forgot to return these to you yesterday. What do we do about that? Well, I'm going to do it the long way first. You don't have to do it the long way. You can skip the middle steps if you know what's going on. Let me give that h a new name. We're going to change it slightly. I'm going to call it h of x equal integral from 0 to x squared, oh, not x squared, just x, 1 plus t cubed dt. That's not the same function. However, I can make it the same. I can say h of x is equal to h of x squared. Nothing up my sleeves, no trickery here. This function, h, capital H, if I plug in x squared, it's equivalent to h of x. All right, so I want to find the derivative of h of x squared. That's what? What does the chain rule tell me? That's the h dx times the x squared dx. Well, the h, I guess I could say at x squared. The h dx, okay, we know what this is. We've been doing these. That's just the square root of 1 plus, I have to plug in my variable, x squared cubed. And the derivative of x squared is 2x. So that's the long way to get the derivative of h of x, little h of x. The short way, just look at this and go, well, this has to be 1 plus x squared cubed. I plug in x squared here. But the chain rule requires I multiply by the derivative of that, so 2x. I think I'm just going to do one more of these. Any questions on what we're doing here? I know this is a little abstract. This is just, we're playing around with the fundamental theorem here. I guess I want to put a little meat on this, though. I mean, you start playing around with variables and algebra, you sometimes lose track of what happened here. So I have this function, I'm calling it capital H of x. Well, let's look at this function, for which this is the antiderivative. Is that right? No, this is just the area function. So I'm going to graph 1 plus t cubed. What does that look like? Well, at 0, it's 1. And the large x, it looks like x to the 3/2. So it's going up faster than x squared. Something like this. So we have some point x here. So if I have a point 1, 2, 4, and 2, 3, 4 here. And of course, I'm finding the area. What am I finding it from? 1? Oh, from 0? Yeah. That's my large h of x. It's this area. What my little h is doing, where we go from 0 to x squared, well, if you take this function and just take the graph and stretch it a certain way, where, one, you get the same point. At 2, you get the value of 4. I'm just going to go right off the map here. 3, whatever you would have seen up at 9. Now we're calculating some new area. So it's just like we're taking this graph and we're stretching it in a, not in an even manner, right? 1 goes to 1, 2 goes to 4, 3 goes to 9. So that's what's happening here. All right, we said I just want to do one more of these. So, you have the function integral from e to the x to 0 sine cubed t dt. Now, again, I think the idea here is to kind of scare the newly initiated, because everything about this looks complicated, but we don't have an x here, we have some new function, e to the x, we haven't seen here. And what's the integral? Cubed, sine cubed. It's even hard to, what does that look like on a graph? But we just have some simple steps we can take. We want to find its derivative. The first thing we can do is we can switch the limits. Right? So if we want to find the derivative of this function now, the fundamental theorem tells us, well, that's going to be negative sine cubed of well, we have to plug in e to the x. But the chain rule tells me we also have to find the derivative of e to the x, which is, everybody knows, e to the x. So that's the derivative of this function.
I have a question.
Yes?
So is the reason it's not like the derivatives don't come out like we normally see them is because we're taking derivative of a function and not just,
I missed the question.
well, because if you were to take the derivative of sine qt, it wouldn't end up being negative sine cubed. It would, but because we're doing functions instead of just what we normally do, it's not the same.
Yes, that is true. I think there were two things packed in there. One of them is whatever this weird function is. Here's 0, and here's, for some x, here's e to the x, right? So the first thing we're doing is we're not integrating this way, we're integrating that way. That's what this is saying. So to get us back to where we know, we just switch the integration. Now we're going from 0 to e to the x, but we end up with a minus sign. So that's the first part. That should be pretty simple. Now, what does it mean that we're going from 0 to e to the x and not x? Well, it's this was my example here where instead of going to x, we're going to x squared. In other words, it's the function we're finding the area under is a different function. Now, it's a composed function. Right? So, I guess we could, again, hand waving here, I could do this. That's really all we're doing. I'm sorry. That was sleight of hand.
No, it's just like if you were to have sine of x, you take the derivative of sine of x, it's going to be cosine.
Yeah, just to be clear, this is where this function is, we're in an integral here.
Yeah, and because you take the derivative of a function, it's not the same as if you were to take the derivative of just a single piece of the function. I'm just a little confused about how you still end up with sine cubed.
Or is this is the formula for the area, right? Not the
I hear your question, I hear your confusion. I'm trying to ask your question again. It was a good question. You're saying,
Why do we get cosine?
why do we end up with sine cubed?
No, because we start with sine cubed, and you take the derivative, and why don't we end up with like cosine cubed?
Oh, okay.
Because that's what you would get if you were to take the derivative.
Yeah,
of the
okay.
function.
So let me write two different things that look almost the same, right? So I'll say f of x equals sine of x, and g of x was the integral from 0 to x sine of x, sine of t dt. And so now I want to know what derivative of f of x is and derivative of g is. So they look similar, right? But we know the answer to this. This is cosine of x. This is just sine of x. Does that get to the, I'm not saying it answers your question, does that get to the heart of what you're asking?
Yeah, because it's an integral, it's not the same as if you were to just take the
Yeah.
derivative of sine of x.
Yeah, we would evaluate this as some f of x minus f of 0. And what is this capital F? It's the antiderivative of this. Well, what's the antiderivative of sine? It's negative cosine of x. I do feel like I'm making this, I'm not making this simple.
We haven't taken the antiderivative yet, have we? We're just taking the derivative of the
Well,
integral.
we're kind of skipping that step, right? When we write this, right? This function is the antiderivative, right? The antiderivative of a function. I have some function. That's this. Some values, some y values. If I instead just pick some starting point, and now my new function is the area under the curve, this is the antiderivative. And that's what makes kind of calculus kind of fit together. You can, we know about functions. We've spent most of the semester looking at derivatives of functions. And that tells us the slope. Now we're saying, oh, if you have a function and find its antiderivative, you can figure out what the area under that curve is. I'm half glad you're scratching your head. This is really, this is really at the heart of, what we're doing here. We're finding that there's two different things. We're thinking about functions. There's two different things we can do with them. We can find this. We can do this operation called differentiation. It tells us like the rate of change. And then we can do this other operation, find the antiderivative, which helps us find area. Now, I have one more thing to say about it, but I know George is tapping his pencil, so he wants to ask a question really badly. Go ahead.
Well, it kind of goes, well, you said you're going to skip out the middle steps. I guess I was just going to ask you instead to do the middle steps that you said you're going to skip out. So
the middle step I was skipping out of was, like, if I have something like this, right? So I can say, oh, this is the derivative of g of x is sine of x squared times 2x, right? So I wanted to show why this pops up, why you get this because of the chain rule. And the way I did it is I created another function, I'll call it big G of x, which was just, from 0 to x, it's sine of t dt. And now I make a composition. Instead of just g of x, I find g of x squared, which of course is this little g. And when I'm finding the derivative of the composition of functions, what do? Derivative of this big G of x squared is going to be the derivative of G at x squared times 2x because of the chain rule. I just wanted to show that's where this comes from.
I was hoping to get you to write what you had, what you erased off the board when you asked your question was the derivative of capital F of x over dx equal sine cubed. I was hoping to get you to write that back up, but I don't know.
Derivative of
Yeah.
f of x dx.
Yeah.
That's just another way of writing f prime of x, right?
And of negative cosine x, is that?
Oh, well, we need to write.
I'm trying to get you to go back to
Oh, well.
the original example.
Well, I guess I'm using these function names a little too inconsistently. How about we start over? So I have an area function, which is the integral from 0 to x of this f of x. So it's just the integral from 0 to x of sine of x dx. Right? So in this case, we can say, what is f of x? Capital F of x. Capital F of x is negative cosine of x plus a constant. That's the antiderivative of this function. So it's the antiderivative of this function. You can also see it as the area function from some starting point to x of our original function. I'm still going to come back to what I left off. Just hang on there for a
No,
second.
it's starting to make sense,
Okay.
a little bit.
Where does the f of b minus f of a come into this? Because that's
Actually, I wrote this wrong. This should just be a dummy variable. This is the real independent variable. Say again?
The middle step that I'm not seeing is the f of b minus f of a, the antiderivative, so it's like the definition.
Okay.
Yeah,
I
maybe
took that down. I'll put it back. That, given that capital F of x is an antiderivative of f of x, right? In other words, you find the derivative of the antiderivative, you get the function. Given that, we can evaluate, this is part 2, we can evaluate this function as capital F of b minus capital F of a. In other words, we can use the antiderivative to find the area. That's that part. All right. I want to. I'm using you as, I'm abstracting you as all students who are sitting here like, what is he talking about? What is this about? And I'm gonna go back to an example I gave at the very beginning of class and then at the very beginning of this whole section. Say this is time, and I'm walking somewhere. And y here is, I'm stuck. I'm like a train. I'm stuck in a line. But I can move back and forth. So I start walking, and I move around, and I get somewhere. So we have this idea of the derivative. Says, well, I'm moving along, not very quickly, and then I pick up, and then I slow down. I don't know, I can't draw this very well. But whatever, this is the velocity, right? Think of it, you're driving in a car, right? You start at 0, you start moving, you speed up, you move along for a while. Well, you're moving in the y direction. Maybe you stop. I don't know. For some reason, you put it in the reverse. But what we're doing is we're looking at where we are, and we're differentiating it with respect to time, and we get a graph of the velocity. Okay, so that's the direction we've gone for most of the class. Now, if I have a velocity graph, all right, I start off, speed up even some more, slow down, maybe go in reverse. All right. Here I'm going in this direction. Now, I have my velocity graph, and I integrate under it. I start finding the area under it. So what does that look like? Well, I'm not going to draw this very well. I'm not very good at manually changing things. But the idea is, I have a velocity. I'm driving along in my car, and I'm sitting here with my calculator brain and going, oh, how long till I get to LA at this velocity? If I speed up, I'll go faster. In other words, I'm going from velocity now back to distance, where I am. Well, how did I do that? I took velocity and I found the antiderivative of velocity. So I'm kind of going in the opposite direction. If you think about it, if both of these graphs are how far I went, and both of them are, the graph below it is the derivative, the velocity, it makes sense that I could go in the opposite direction. The only thing you really lose when you go in the opposite direction is you don't really know where you started. If you know where you started, then you do know. But if you just have a velocity graph, you don't know where on the x, well, I'm calling this y, you are. Yeah, I'm scratching my head too as to how to impart this. There are these two pieces here. There's like what's going on. We've got velocities, we've got areas. How are they connected? And then there's just the mechanics of it, right? We've done an awful lot of mechanics. We found that if our function is some monomial, then its derivative is x n minus 1. We know the derivatives of various interesting functions like the trig functions, hyperbolic functions, exponential functions. We have some rules, like the product rule and the quotient rule and the chain rule. It tells us if we have some complicated function, how can we find its derivative? Now we're trying to go in the opposite direction, and it's not so mechanical because you don't always have an antiderivative. a lot of the next course after this is looking at different ways to find antiderivatives that we're not going to cover. Mostly, we're just using what we know, right? We know we can go from, to find the antiderivative of this, we can go here, but this isn't a very pleasant way to look at it. We want to say if f of x equal to x to the n, and if we want to find the antiderivative, right, we're going to go to x to the n plus 1 over n plus 1. You know, it's just a formula. It's just a way of simplifying this. All right, I don't know where else to go with this right now. We have a new subject to cover, but I'm just hoping that yeah, I'm going to ignore that. Well, I guess in doing these examples, I was showing you where we invoke the chain rule when we're trying to find something. No, I don't think it's worth doing that. Okay, I guess we'll take a break for a few minutes. I'm quite sure 2 flights down in the cafeteria they will. You want to go run and get some? Go for it. Don't start without it. Okay, all fixed. All right. Second half of the class will be a little bit more straightforward, I think. We have this idea of you have a function and an antiderivative, which is just the function whose derivative is our original function. And we have this from the fundamental theorem, we have this nice feature that if we have a definite integral, digression here, one could come to the conclusion from either reading the book or things I've said that this represents the following. Which we sometimes write this way. Sure, yeah, this will calculate it if you can find the antiderivative. But this notation really means the area under this curve. There may not be an analytical antiderivative. We can always use, nowadays, we can always use some mechanical method, a computer or a calculator, and we can get at least an estimate, a good estimate of this. But this represents the area. This is how we can calculate it. Now, we've been just calling this the antiderivative, but for some odd reason, the book kind of does things in a funny order, and I've been following the book, and we have a name for this, and it's called, well, we have a name and a notation. And we write it this way. We just write it the integral sign without limits, the function, and we call it a definite integral. I guess I want to write this up here. Definite integral. I'm sorry, I'm so confused. It's not called a definite integral, it's called an indefinite integral. And it's the antiderivative. For those who are interested, this is section 5.4 in the book. So, for example, if we want to find the indefinite integral of the function x, we have a formula. We know this is x squared plus 2, x squared divided by 2 plus a constant. We always add a constant because if you find the derivative here, that constant goes away. And again, we might write this as I guess what I want to say is that the connection between an indefinite integral and a definite integral is that you can find the indefinite integral, and if you have a definite integral, maybe x dx, you can calculate it as the difference in the antiderivative at one point minus at another point. All right, this is, I know I'm repeating myself, and I'm going to a bit here. So we have a whole long list of well-known antiderivatives. X to the n polynomial is just x to the n plus 1 over n plus 1 plus c, noting that x cannot be equal to 1. Negative 1. So that, of course, would give you division by 0. However, if you happen to have x to the minus 1, which is just 1 over x, we know that that's the natural log of x, or actually the natural log of the absolute value of x. I'm going to try to go through these pretty quick because we've gone through these before. E to the x is just going to be e to the x plus a constant. All the functions that we found derivatives for, you can just go in reverse. So integral of the sine, of course, is the negative cosine. Integral of the cosine is just the sine. Secant squared, you'll recall, going backwards, is tangent. Secant squared times the tangent be the secant. Just take that list of derivatives you brought to the last exam, maybe, and just kind of run in reverse. Roll 1 over the square root of 1 minus x squared. That's going to be our inverse sign. Integral of 1 over 1 plus x squared. That's going to be our inverse tangent. Hyperbolics are going to be pretty obvious. So, along with this long list, we have some rules that can make things easier. You have the integral of some constant times a function. You can just take the constant out. We saw the same thing with derivatives. Constant times a derivative is just derivative of a constant times a function is just a constant times the derivative of the function. The same is true for an indefinite integral. Likewise, integral of the sum of two functions, just the integral of the sum of each. So these are formulas that that can help us evaluate indefinite integrals, antiderivatives. Now, keeping these in mind and thinking about chain rule, you can deduce certain other patterns that you can look for. So, for example, since you know the integral of 1 over x is the natural log of the absolute value of x, well, if you happen to see 1 over some function, and happily it's multiplied by its derivative, that this will be the log of the absolute value of that function. If that's not apparent, just start over here. What's the derivative of the log of f of x? Well, it's going to be 1 over f of x. But the chain rule is going to say we have to multiply it by the derivative. So that gives us this pattern. An example might be useful right now. What if we wanted to find the indefinite integral of x over x squared plus 1? Well, we look at the denominator and we say, oh, what's the derivative of x squared plus 1? It's 2x. Well, that's not what we have in the numerator. But that's pretty easy to fix. We just put in a factor of 2 here and a balancing factor of 1/2. And that's going to tell us this is 1/2 the log of absolute value of x squared plus 1 plus c. Now, it's a good time to note, clearly we don't need the absolute value function here, because this is always going to be positive, so we can just write it this way. Questions? I'm kind of barreling along here. I hope this is straightforward. All right. Another pattern we can make use of is, since we know that the integral of 1 over 1 minus x squared is the inverse sine, if we were to find something that looks like this, derivative of f of x over square root of 1 minus f of x squared dx, you can see that that's going to be the inverse sine of f of x. Again, if it's not obvious why that's the case, just find the derivative here. Derivative of the inverse sine of some function. Well, I'm going to have to plug that function into this expression. 1 over 1 minus square root of f of x squared. But the chain rule requires I multiply by the derivative. So again, let's take a look at an example of that. We have the integral of x over the square root of 1 minus x to the 4th. Well, the f of x we see here is x squared, right? X squared squared is x to the 4th. Its derivative, again, it's 2x. We can fix that. We can just put in the factor. And so we'll get that this is 1/2 the inverse sine of x squared. This takes a lot more work than finding derivatives, because you have to kind of see a pattern, see something that looks plausible. You can always just try something. You can just always say, well, it looks like it's going to be x squared. Find the derivative, and then you can see you need a balancing factor of 1/2 to make it work. A very similar pattern is f prime of x over 1 plus f of x squared, which if you look over at the derivative of the inverse tangent, you'll see this has to be inverse tangent of f of x. So the way you get some confidence with these is you do a bunch of homework problems. And the ones you can't figure out, you bring into class and we go over them and you practice them a little. again, unfortunately, it's not as straightforward as finding derivatives. And I guess I'll do a little foreshadowing. We're gonna learn one more technique for finding indefinite integrals, antiderivatives in this class. There are 3 or 4 others that you'll run into in Calc 2 if you take that class. Okay, I just have 2 more problems in mind here I want to go over. One of them isn't really all this tricky if you just kind of see it for what it is. But you may run into it in this class. Let's say I wanted to find the integral of t to the 5th minus 4t cubed plus t squared minus 8t. Where did I come up with this? T squared dt. I'm going to find that indefinite integral. Well, certainly this is not going to be the derivative of what's in the denominator. So that strategy, looking at that pattern, it's not going to work. But we're free to use some algebra here. And we can rewrite this. We can simplify this. This just becomes t cubed minus 4t plus 1 minus 8 over t plus 5 over t squared. And since we know we can break this up, by the sum and difference, we can do each of these separately. So for 1, 2, 3, 4, we're just going to use the reverse power rule. It's going to be t to the 4th over 4 minus 4 t squared over 2 plus t. We'll come back to this one. Okay, so 5, this is t to the minus 2, so it becomes t to the minus 1 over minus 1. All right, what do we do with 8 over t? Or 8 times the minus 8 times 1 over t. What's 1 over t? What's the antiderivative?
Natural log.
It's the natural log. T, the absolute value of the natural log of t. Nope. Don't forget the constant. So if you see something that looks like this, it makes sense to simplify, the fraction here, break this up into pieces and see if everything works. As soon as you add something like this, well, we're not going to cover this, but I will point out that it looks a lot like this, doesn't it? There's a technique called partial fractions that will solve this, but not to be covered here. That was one. This is just kind of a pattern matching puzzle. I'll let you think about this. See if you can come up with the answer on your own. this were, whenever I say something like this, I think to myself, oh, come on, Mr. Schongren, you're just baiting us. But if a problem like this were to appear on the final, it would probably be towards the end, one of the more difficult ones. Not because it's that difficult a problem, but just it's the kind of problem that, under the stress of an exam, might make life difficult. Okay. Let's spend a few minutes thinking about it. Right. If you haven't seen it yet, you might want to note that e to the 2x, that's really e to the x squared. And you might note that e to the x is also the derivative of e to the x. Anyone want to throw out a... I saw that hand. Yes, what do you think it is? What do you think it might be?
It follows the pattern of the arc sine.
Yeah. That instead of x, you've got some function which happens to be e to the x. So, okay, you've already given it away, so I'll ask someone else, right? Anyone else? What would be, yes?
I'm going to try my best here. I'm guessing e to the x times sine, or inverse sine, of e to the x plus c, the constant outside there.
Okay. This helps me understand how difficult this is. It's not quite. We've got all the elements here, but does anyone else want to?
He said inverse sine of e to the x, not
Yeah,
like
like e to the
So e to the x times inverse sine e to the x. That,
Like that?
with e to the x.
Yeah. Now, let's say taking the final and you're trying your best and you're thinking, I don't know, maybe, but you know, I don't really give you a lot of pressure, so you might want to think, well, all right, what's the derivative of this? Well, we would have to use the product rule, so it would be e to the x times the derivative of inverse sine of x plus inverse sine of x times e to the x. it's not what we wanted, right? So we have to think about it a little more. It was introduced in, I was teaching freshmen in high school about doing algebra, and we had this idea called guess and check. It wasn't exactly what we're doing here, but sure, all right. It's a good guess. We have a way to check it, it's not right. But again, if we can figure out this is what it is. All right, so inverse sine of e to the x, that's 1 over square root of 1 minus, well, we have to plug in the e to the x, times the derivative of e to the x, because of the chain rule. And that's what we were looking for. All right, that's all I've got for today. Yes?
So you can just like substitute the values, correct? Like e to the x, you can take e to the x is e to the x. And then solve for x.
Rather than try and talk over the noise, I'll let people want to get up and go, and then anyone who wants to stay and listen to what your has to say, as I do. Questions? For you for a few minutes. You can be up here if you want, or we can go down to my office. I apologize, I'm going to take up a few more minutes of your time, but I have to talk to you in private.
Thank you, Professor.
Yeah, it's not that you need to be in private. You need to be in private.